right? So first thing we want to know, the period of the function. So what was the period of the sine function when we graphed it? You saw in the investigation, all those different things. Vito? No. No. Joy? 2 pi. Okay. Does anybody know why the period of the sine function would be 2 pi? George? It doesn't necessarily, it does, but it doesn't. It's not determined by the y values and the difference between the maximum and minimum. Henry?
It's where the pattern stops.
Okay, good. It's where the pattern stops. Why is 2 pi the special number where the pattern stops? Jonathan? Because it's also when it starts back up again. So take a step back and go back to unit circle world, right? When you calculate the sine of any angle between 0 and 2 pi, you go to that angle around the circle, you get the sine value, okay? What happens when I do the sine of, let's say, 5 pi over 2? Is that more than one time around the circle? Yes. Okay. Was there a place I could have landed my first time around the circle that is the same position as 5 pi over 2? Yeah, pi over 2, right? So once I've gone through the whole every angle and I'm back at 2 pi, I can keep plugging in angles bigger than 2 pi, but are they ever going to land anywhere different than where they had landed before? No. So all the values I got before are just repeating and in the same order because I'm continuing to plug things in numerical order, which means they just keep going around the circle in that same direction. So does it make sense why the period of the sine function is 2 pi? Okay? Yeah, Foster.
So does it originally start at 0 then?
Well, we can measure the period from lots of different places, okay? But 2 pi is how long it takes to cycle it around, because even if you didn't start at 0, let's say you started at pi over 2 on the unit circle and you looked at the sine there, you wouldn't go through the same exact values in the same exact order until you got back to pi over 2 again and started going around the circle second time. So it still took you a whole lap around the circle to start repeating those values in the same order. So a whole lap around the circle is always 2 pi. The distance 2 pi is the period, okay? So then the sine function, what is its amplitude? Test it. 1. Okay? So the maximums and minimums of the function are no more than 1 unit away from the middle of the function. So this actually comes back to a test question on our last test, right? I didn't finish grading it yet, so I don't know how close you guys were to getting it. Why can the sine calculation not exceed 1? Why can't it be at 2 or 5 or something else? Ian? Okay, so less to do with the radius of 1. I like the poll, okay? But less to do with the radius of 1, because remember, sine is not a single number. It's a ratio between two numbers. Why can that ratio not exceed 1? Hannah? Okay. Okay, so partially yes. Sine is the y-coordinate because we're in a unit circle. So it's not really just the y-coordinate. It's really the y-coordinate over something else. Will? Okay, so if we think triangle world, right, we calculate the sine by doing opposite over hypotenuse. In order for that to end up being more than 1, that would mean the opposite, the numerator of the fraction, was bigger than what it was being divided by, which is the hypotenuse. Would that ever happen? No. Okay? So opposite over hypotenuse was one way we looked at sine in triangle world. What did we say the ratio for calculation was when we looked at it at a coordinate plane and with a circle? Foster? Y over R. Okay? If you're on a circle, even if it's not the unit circle, okay, so you guys were like part right, but then we have to like make sure it makes sense in the broad idea. Even if I'm not on the unit circle, but I'm on a circle and I go to a position, can the y-coordinate at the position ever be bigger than the radius of the circle? If you're on the circle, can your y-coordinate ever exceed the radius? No. The closest you get is when it equals the radius, right? Okay, and in our case, when it equals 1. Okay, so from both perspectives, either of those are good reasons, but we should fully understand why the sine value can't exceed 1. Right? And that's why a lot of you guys, when you were trying to do inverse sine or inverse cosine on your calculator, and you were trying to take inverse sine of something bigger than 1 or inverse cosine of something bigger than 1, it was saying error. Because you're trying to ask it at which angle it has this sine or cosine value that's bigger than 1, and it's saying nowhere. Like, that doesn't make sense because the sine and cosines can't be bigger than 1 because of what they are, right? The way that they are calculated, okay? So knowing that the sine function has an amplitude of 1 and a period of 2 pi, I'm going to build the parent function. So I have this well memorized as far as where you should get in the future with this. Knowing that the period is 2 pi, I generally mark the fourth mark on the graph, the 2 pi. Why do I do that? Because there's 4 points along the way that are very easy to calculate before I get there. So I like that one to be in that position because it splits up well that way, okay? And that tends to be true for all the functions that we graph, okay? Now, what does that make each tick mark on my graph equal to? Kira. Not pi over 4. Close. We are going to divide by 4, but when we divide this by 4, it ends up being pi over 2. Okay, so each tick mark on my graph is pi over 2. So if this tick mark is 1 pi over 2, the next tick mark is 2 pi over 2, which reduces to pi, and then 3 pi over 2. And then I should feel real happy about myself because here it would be 4 pi over 2, which is 2 pi, so I have a little confidence that I was doing the fraction math correctly, right? And then it would be 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2. Okay. Then I have memorized the sequence or the order in which the sine function flows. Just like you guys know the parent function of a quadratic, that its vertex is at 0, 0, and it goes over 1, up 1, over 2, up 4, right? You guys know that pattern of points based on your experience with quadratics. Now we know the patterns and the distances between the points for the sine function. Where does the sine function start at the origin? 0, 0. And if you ever forget that, if you mix up the sine and the cosine, literally plug it in. You're at 0. What is the sine of 0? 0. So that's why the point starts right there. Okay? And if you plugged in these other values, you would get at pi over 2, it's 1. Okay? But we're going to make sure we have it memorized. So there's one period of the sine function. And if I want to graph more than one, which you do because it does forever go in each direction, then I just continue that pattern of points to the rest of the graph. Okay? Are we all right with the sine parent function? Okay, and that's with this being 1 and negative. You okay? All right, so let's look at the cosine parent function. If you move the axes out from behind them, you can't even tell them apart, right? They both have like the same shape. They reach the same maximums and minimums. So what's the period of the cosine function? What's the period of the cosine function? Gus? Good. What's the amplitude of the cosine function? Foster? 1. It carries the same idea as the sine function, right? You're not going to recycle back through, but you go once around the circle, you start hitting all the same things you did before. The cosine is never going to be bigger than 1 because it's adjacent over hypotenuse, or x over r. So all the same ideas apply to it, okay? So again, period is 2 pi. Gives me kind of the same numbering idea on my graph. But sine and cosine are not the same thing, right? So what differentiates them? When we were looking at the unit circle, we were saying, oh, this one's the x, this one's the y. Now, when we're looking at the way they're calculated, they do hit all of the same numbers, right? They all hit 1/2, root 3 over 2, root 2 over 2, 1, 0, negative 1, all of that. But at 0, is the cosine equal to 0? No. So it hits all the same numbers, but in a different sequence or order because we're looking at a different coordinate at that position. So what is the cosine at 0? 1. Okay, so that graph starts here, but then cycles through the same values of points. So it'll still hit those 0 marks and negative 1 and 0 and positive 1. So the cosine parent function looks like this. And again, to extend it to a different period, I would just extend that specific pattern of points hitting each of those locations along the way. Oops, except for you have to actually go through the points and graph it. Yeah. Okay? So sine and cosine, super similar, just about where the pattern is kind of starting, so to speak. Okay? Are we good with those? Okay, and then the tangent is like totally different, right? Like way different visually than what's happening with the sine and cosine, yet still periodic. It looks much different, but it still cycles through these different values. Okay. What was the period of the tangent function? Joy. Pi. Okay, why the change? It still takes 2 pi to get around the circle, right? Anybody have any idea why the tangent function would only take pi to cycle through its values before it starts again, even though to get all the way around the circle still takes 2 pi?
Would it be because I was thinking that when you had it graphed, you had the lines that were just basically asymptotes going through, so it would just cycle up to that one point and stop at some point.
So yeah, that's visually how it looks, but why does the calculation do that? Why does it only take pi instead of 2 pi to get from one of those asymptotes to the other? Hannah?
It's taking the ratio of y over x.
Yeah. So first of all, it's much different, right? It's not just the x coordinate each time or just the y coordinate each time. It's dividing them, right? So think about your unit circle and how that works out. First of all, one of the reasons the sine and the cosine took 2 pi, the sine went through all the same values. It does this, right? It goes through all those values. So it goes through all these values, and then it goes through them again in a different order. That's how it has like the symmetry of looking like a parabola. Then it goes through all the negative versions of those values and them in a different order. And that's why it takes 2 pi instead of like 1 pi for the sine to get back, because it goes in different orders and it takes the positive and the negative. But think about the tangent kind of simply. You don't have to write this part down. But in the first quadrant, when you calculate the tangent, is it positive or negative? And then in the third quadrant, positive. And then in the fourth quadrant, negative. So already right there, okay, this kind of helps us in the fact that, notice, sine would have been positive, positive, negative, negative. That's why we would have to go all the way around to start getting the same numbers in the same order again. Cosine would have been positive, negative, negative, positive. So because it's not mirroring itself, it goes all the way around. But basically what's happening in the tangent is when you start calculating the tangent of each of these spots as you go, you get answers and different answers. You get positive ones. Then you start getting negative ones, okay? And then you get here, and guess what? You start getting those same positive ones in the same order that you got right here, because the first one you hit here was a 30, you hit a 30. You hit here a 40, you hit a 60, you hit a 60, right? So you start hitting the numbers that would give you the same results. And because the third quadrant's positive just like the first quadrant, and the second quadrant's negative just like the fourth quadrant, you get through all the same values that you had just calculated right here in the same exact order. So that cuts the tangents period down by pi, because it only takes half the circle to cycle through every possible tangent value and then start doing it again. Okay, so does that kind of give you an idea of why that would happen? Yeah, Jonathan. No, so what happens is the order that they do it in. So like the x coordinate here, so let's think about cosine, right? So the x coordinate here is 2, right? Then root 2 over 2, then 1/2, then 0, then negative 1/2, negative root 2 over 2, negative root 3 over 2, negative 1. Then this one is going to be negative root 3 over 2 still. So the thing is, it's not going back to the beginning of this cycle and going through them in the same order. It's going to go back through all these numbers this way, but that's not same numbers, same order once you hit that spot. Does that kind of clarify a little bit? Okay. All right, so our tangent function only has a period of pi. That means this time, for those 4 convenient points, I'm going to stop that numbering at pi on that 4th mark. Which means, what is 1 tick mark equivalent to on my x-axis? Foster? Good. Pi over 4, because I divide that by 4. So if this is 1 pi over 4, then the next one is 2 pi over 4, and then 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. Okay. So what you saw on your tangent graph, and when you plugged in some of the points, is that when you plugged in 0, you got 0. Then you plugged in pi over 4 and you got 1. Then you plugged in pi over 2 and it was undefined. Okay, so that meant the graph can't cross through that, because if it crosses through, there's a point there. A point there means you plug this in and you get that answer. We don't get an answer. So to mark the undefined, we marked these asymptotes on our tangent function. So what happens is this value just keeps climbing like that, getting closer and closer to the asymptote, but never crossing it. Then when you plugged in 3 pi over 4, you got negative 1, and pi you got back to 0, and that meant that this branch gets closer and closer to that asymptote that way, but never crosses it. So this is one period of the tangent function, but I have no real mathematical reason for this except for that this is very not visually appealing to me. That when I do my tangent graphs, this is not what I graph as one period and do my transformations. I actually use the rest of this piece over here. I find it so much easier to start with this. I don't know if it's just the way my brain works or what, but it's so much easier for me to start with this like confined amount between the asymptotes and transform all of that and then copy it than this like half of this curve, the asymptote, half of this other curve. So when we do our tangent graphing, I'm always going to start with this period. It's still pi, because pi over 2 added together is pi. So I'm still doing one period of the graph. I'm just not starting it from 0 to pi because I find it simpler to start with this part right here. Foster?
So it doesn't matter what part of the graph you do as long as you start with
As long as you have a whole period of the graph. Okay? So are we good with our parent functions? All right? Questions? Yes, sorry. Thank you. I should label my axes much better, especially being the teacher of the graphs. Okay. Are we good with our parent functions? So what we're going to do is we're going to walk through one graph that has a bunch of transformations together, okay, through each transformation individually. And then you guys are going to look at 3 other sine and cosine graph examples at home this weekend. And then Monday you're going to dive in and like start graphing ones that have more than one change. Last night's graphing was very much like, can you just remember or learn from this investigation? This one number does this. This one number does this. And now we want to be able to perform all of those things on one graph. Tustin? Oh, yeah. Okay, let's talk about that. Good. It's not infinity because an amplitude is a specific measurement, so it's kind of technical. Amplitude is technically measuring from like the midline of the function to the maximum, which means to have an amplitude measurement, you need to have a maximum or a minimum part of the wave. You need to have both. Because this wave has no maximum or no minimum, we don't say the amplitude is infinite. We say there is none. Like this physical measurement cannot be completed. There is no way to measure this physical thing because that physical thing depends on a maximum and a minimum in a set of waves. Does that make sense? Okay. Thank you for asking. Okay, are we going to try one? Yes? No? Maybe? All right, let's see. We're just going to do this. Oh, yeah. Okay, we're going to talk through this, but I'm not going to write it out. If you need to write it out, write it out. You did this in your investigation, chunked up by part. If that's my equation, so let's see if you guys learned from your investigation. If that's my equation, what does A affect? George? Reflection? Okay, so if A is negative, we have a vertical reflection. That's one thing that A affects. What else can A affect? Vito? It could also do a stretch or compression, okay? B, what does B affect on my graph? Hannah?
That affects, if it's a negative, then it's a horizontal reflection, and the number is a horizontal compression or stretch.
Perfect. So if it's negative, there's a horizontal reflection, and the numerical part of it would cause a horizontal stretch or compression, okay? And we're going to deal with those pretty specifically. We're basically going to, instead of physically taking our graph and compressing it or stretching it, because sometimes the numbers are weird, like you numbered by pi over 2, and then like the period needs to be 2 pi over 3. It's like, oh, how do I relabel the graph that's already, so what we do is we just like erase the numbers and renumber it how it wants, so it doesn't look like we did anything, but if you look at the number, then like you know you stretched or compressed it because it ends in a different spot than it did before. Okay, yes, it's like cheater method. Okay? All right, what about H? Aiden? Awesome. Horizontal translation. So shifting the graph left and right. And the number might look gnarly sometimes, like pi over 6, but pi over 6 is a measure of a radian, and that's how you've labeled your axis, so that's going to be fine. And then what about the K? Kira? Good, vertical translation. So the entire graph shifts up and down. So know the difference between amplitude and vertical translation. Vertical translation takes the entire graph, including the points in the middle of the waves for sine and cosine, and moves them up or down on the coordinate plane. But they keep their distances apart. A vertical stretch, the middle stays where it was, and the maximums and minimums are pulled further away, or in a compression, scooted closer to those points in the middle of the function. Okay? So we'll talk about this in a little bit as we go through about amplitudes and all that kind of stuff. Okay? All right, so first thing, here's an equation. Okay, so if you have your note guide, this is in there, and it has step by step for you to get through the graphs. That's what we're going to do, okay? So the first thing it says is to rewrite it in this fashion. The reason this is not technically considered this fashion is because this 2 has been distributed to the x and to that, so I'm not seeing the true horizontal shift if I leave that number as pi right now. So I'm going to rewrite it in its factored form. I'm going to write it here because I don't have room up there. So negative 2 sine, factor the 2 out from the x and the number, and then plus 1. What's going to be in the parentheses after the 2? Ian? Good. X minus pi over 2. Okay? So then step 2 says graph y equals sine of x. You're going to start with your parent function. That's not surprising. That's how we've done all transformational graphing, right? So my parent function had a period of 2 pi. We just looked at it. You can look back a page if you need to. The sequence of points went like this. Those are 1 and negative 1. Okay? That's just the parent function. That's all it is. Okay? I didn't number all the other tick marks yet because I'm not sure I want to, because I'm waiting to see if there's a stretch or compression, and I might want to renumber it a different way. Okay? All right, so the next thing says to graph this. Okay, so this 2 is going to do what to our graph? Yeah, Brian. Hi.
I have it for Nick.
Nick. Nick's got a big baseball game tonight.
Yeah, it's at Angel Stadium at 6:30.
Yay, Nick. Angel Stadium people. Oh, and you get a round of applause, Nick. How lovely. Okay. Oh, wow. And it's all on the recording. It's good. Okay. All right, refocus. All right. So the 2 there is going to do what to our graph? Vito. Good. A horizontal compression by a factor of 1/2. So think about it. That means horizontal lengths are getting multiplied by a factor of 1/2. What currently is the horizontal length to get through one cycle of the sine function graph? 2 pi. That length is changing because we're changing the horizontal lengths. So the period is going to get affected every time by this number. How you've done your horizontal stretches and compressions in the past. You take what you normally know to be the length that it takes to complete the cycle. You multiply it by the factor of your horizontal stretch or compression, and you end up with what the new length is to complete the cycle.
So since it's like a horizontal, you just take the reciprocal of whatever.
Correct. Mm-hmm. So instead of me physically redrawing my graph so that this point at 2 pi ends up at pi, meaning I have to go like faster through all those points, and then I have to renumber my tick marks, this one's not that bad because splitting halves and halves is not too bad. Splitting something like 2 pi into 2 pi over thirds and like changing where those are gets a little bit crazy sometimes, so this is how we do it. I just go and make the 4th mark equal to pi, and then I make the same graph that I made before. Right, it's not cheating. People just need to read what the graph says on the labels. If anything, it teaches you how important it is to read the scale of your graph, because it doesn't look like I did anything, but I totally did. Okay? Right? Now I'll number the rest of my graph. Now that I know that's the period, it takes that long to complete it, and I know that that's the cycle for the final result here, which means each tick mark on this graph is going to represent pi over 4. Okay? Because the period is now pi. The 4th mark I have on my graph is pi, which means I want each other mark to be a 4th of that, pi over 4. So then 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. You get the idea, okay? Are we good with that transformation? So really the way that we're doing it, your stretches and compressions aren't going to look visually like your graph changed, but if people pay attention to the numbers, like we should if we're reading graphs, they would understand that it did change, okay? All right, so now we're going to do this transformation. So here's the new part of it that we're putting in there. What kind of transformation is this? Vito told me the last one. Foster answered the question before that. Aoife? Good. Am I going to the right or to the left? Going to the right, pi over 2. Now I need to go and read my graph, and this is why it was important that I now went back and numbered each tick mark. What really is pi over 2 on my graph? So if you look at the way that we numbered it, right, how many tick marks does it take to get to pi over 2? 2, right? So I'm basically shifting my entire graph over 2 tick marks on my x-axis because 2 tick marks represents, in my measurement, pi over 2, okay? So I'm going to go ahead and start my sine wave here instead of at 0, 0. I've shifted to the right and go through the same sequence of points because I haven't made any other change. Are we okay with that transformation? Yes. All right, so your next transformation is to deal with this, which is actually 2 transformations, okay? But given that we had a whole semester where we transformed graphs, I think we can do these 2 at the same time and not be too confused. But if you have to do them separately, there's no like pride factor in that, like, oh, I can't do it because I can't do them together. No, then do them separately, okay? And make a separate graph. It's fine. So what is going to happen to our graph with these transformations? Jonathan. Vertical stretch by a factor of 2. So it's going to reflect and stretch by a factor of 2. Now, what that means, the points that were in the middle of the function, along the midline, okay, the part that divides it into equal waves above and below, is that affected by this? No, they aren't reflected because they're on the axis. They aren't stretched because they are what you are stretching from, okay? So these points are not moving from your last graph, okay? However, there was a point right here on your last graph. It was a maximum. It will now be a minimum, okay? And instead of being 1 unit away from the midline of the function, it will now be 2, okay? So that point's going to get flipped over and be at negative 2 instead of positive 1, okay? And the point that was right here at negative 1, it's going to get reflected up and then stretched so that it's 2 units away from the middle of the function. Sin. We're going to do it at the end. I would only do my transformations on one period. Otherwise, it gets very tedious and sometimes confusing. But once we get to the end of the graph, I will then fill the rest of my graph with what this sine function looks like. I'm just not done yet. Okay. So we have one more transformation to do, and that was the plus 1 at the end of the function. What is the plus 1 at the end of the function going to do? Kira. Good. Move it up 1. Now, that means the entire, not some points go up higher than they were. The entire thing, the maximums don't get further from the middle than they were. The middle goes up 1. Okay, so do the maximums and so do the minimums. So on our graph, let's see. We had the middle of our function marked on those 3 points. That's now going to be at 1 because we're taking the whole graph as an entity, okay, one thing, and moving it up 1. So those points will now be here. Okay? And then that minimum point that was at 3 pi over 4 is still 2 units below the midline. The midline just happens to be happening at 1 now. So to be 2 units below this is to be at negative 1 instead of negative 2. Okay? The maximum is still 2 units above the midline, okay, but that means now it's at positive 3 instead of positive 2 because I've bumped the middle up 1. Okay? So then this is my graph. Okay, so then what I would do is to graph the sine function and to symbolize that it continues forever. We wouldn't draw just this portion on only part of the graph. That would make people think that it stops. We would continue. Okay, and if you make your own graph, I want at least 2 periods of the function. Okay, then we're going to go ahead and we would just follow the sequence of the pattern of the points. And then we would have our complete graph. Okay? And we should be able to tell people about the period. So what was the period of this function? You calculated it in your first step after the parent function. So what was our period? Sandy? Good. For this one, it was pi because we had that adjustment that we made, right? What is the amplitude of this function? 2. Remember, amplitude is not the point that it reaches. It's how far those maximums and minimums are from the middle, right? So they're 2 units from the midline of our function. The amplitude is 2. that will match this numerical value here because you're starting with 1 every time and then you're timesing it by that. So 1 times that number always ends up being that number, and you'll see that relationship. Okay. What is the domain for a sine function? All real numbers. Okay. And then what is the range for this graph? Sandy? So -1, less than or equal to y, less than or equal to 3. And in our interval notation, that would be from -1 to 3, including both of them. Okay. So tonight, not on separate graphs, but I just kind of go through a couple situations where, like, some things that might throw you for a loop in the homework show up, that whatever. So there's 3 graphs. It's fairly quick, like around 10 minutes or so. And you just have to write something you learned at the end or a question that you still have, so I can address that on Monday. And so your homework is just to watch those graphs and go. And then on Monday, you'll be in class working on graphing sine and cosine functions. Okay? Tangent's going to work the same way. We're just starting with a different shaped object. Okay? And then for our reciprocal graphs, it's kind of cool. We don't actually graph the reciprocals. We graph these because, like, the cosecant is the reciprocal of the sine, right? So there's a bunch of transformations to a cosecant graph. You pretend like it's a sine graph. And then you basically go like, what would the reciprocal look like? And so it'll be kind of cool. So my point is, if you guys get really good at graphing the sine and cosine function, that should transfer over to the tangent, okay? And then that will make the reciprocal graphing really easy for you guys, okay? All right? So make sure we learn that.